Hello and welcome to Fouraye Education. Today we're going to be teaching financial mathematics. And in this episode, we will get into a little bit of stochastic calculus. We'll be looking at the Ito integral. Now last time we saw that in fact the Brownian motion has a quadratic variation value equal to that of t. Therefore, we can't simply integrate a simple process with respect to the Brownian motion in the means of a Lebesgue integral. So if you look at this, say, so I'll start with the Ito integral where we have a simple process. A simple process being a, being a step function. So we'll not be looking at integrating general processes in this episode. In fact, we'll be looking at it in the next episode. So a simple function is just a step function. We'll be integrating this step function. Now, how do we make sense of d omega t? D omega t is in fact the increment, right? So what we do in order to find such a integral is that if you have the simple process t, what we're doing is first of all let's define our simple process aside from it being a step function. Our simple process delta t is a process adapted to the filtration f of t, and it's going to be associated with the Brownian motion omega t. Now, for each interval of the partition which we will be making, for each of these little intervals, the simple function will be constant, aka it'll be a step function. Now, we will be looking at how we integrate said simple function, simple process, with respect to a Brownian motion. And if we can do that, we'll be able to approximate general processes to multiple smaller simple processes and then find the generalized Ito integral. But first, let's look at how we can make sense of the Ito integral. So, how do we make sense of the Ito integral? The Ito integral is simply, the Ito integral is simply a summation of the simple process Tj times the increment plus delta Tk. So we can say that this is the Ito integral, right? But what is, I gotta add omega t minus omega tk. So what is actually happening here? We're taking a summation from 0 to k minus 1 of these. Because if you look at the timeline, these are all past events. We're at t currently, and t lies between tk minus 1 and tk. So we know all of this, as such we're taking the summation of the simple process with respect to the increment of the Brownian motion. So we're simply multiplying the simple process by the increment and taking the sum. But in this section, now that we're at time t, at time tk, we've already attained a value for said simple function. And as such, we will not be looking at, oh, by the way, it's tk to tk plus 1, not tk minus 1 to tk. So what we'll be looking at is that, well, as you can see, the increment, instead of tk plus 1 minus omega tk, since tk lies between tk and tk plus 1, what we'll be taking is omega t minus omega tk, and that's why this is separate from that summation, because this summation is simply these increments times the simple process's previous value, aka tk, for example, tk times tk plus 1 minus tk. That's what we usually do. But however, in this case, it's tk times omega t minus tk, because we aren't exactly here, we are here, and we take the current value of the Brownian motion in order to attain an increment for said thing. And that is simply how we look at an Ito integral. So, the Ito integral of a simple process. What are the properties of an Ito integral? Now, the Ito integral itself is a stochastic process. And secondly, the Ito's isometry property, which is quite an important property and will tie into the quadratic variation later on. But actually, before this, we said that the first property of the Ito integral is that the Ito integral is a stochastic process. And also, the Ito integral is a martingale. I will not prove this. So, yeah. And the third one of the most important, is Ito's isometry. Now, what is Ito's isometry? The expected value of the square of the Ito integral, which will denote I squared t, is but simply a Lebesgue integral. And in fact, it's going to be dp. So what this is in fact just integral of 0 to t of this. This has got to be another variable. So it's just a Lebesgue integral, which we can solve through simple integration means. A noteworthy thing about the Ito's isometry is that I squared t itself is an element of the L2 space. As such, we can say that this is, well, basically Ito's isometry. So what we got from Ito's isometry is that the expected value of the Ito integral squared is going to be but a Lebesgue integral of the simple process squared du from 0 to t. Alright, so let's move on to the quadratic variation of the Ito integral. Now the quadratic variation itself is going to be a stochastic process. And it's in fact going to be equal to this. But I want to note that yes, the quadratic variation is a stochastic process. However, if you look at Ito's isometry is not a stochastic process because it's the expectation of said value. So while the quadratic variation of the Ito integral is a stochastic process, the expectation, aka the Ito's isometry, is not a stochastic process. But the quadratic variation itself is a stochastic process. Now that we know how Ito integral works on simple functions, we can later move on towards how Ito integral works for a general process. And I'll do that in my next episode. Thank you for listening. I hope you like and subscribe.